And now spectral analysis of the discretization problem. Here we develop the von Neumann method, useful in a wide range of circumstances for the study of difference problems with initial conditions. Let us consider the following problem. In a plane D, capital D, which is equal to t greater or less or equal to 0 and x is between minus infinity and plus infinity, we need to find a function phi of t x which satisfies the equation d phi by dt plus u d phi by dx is equal to 0. And the boundary conditions phi of 0 point x is equal to g of x. X is between minus infinity and infinity. Let u be greater than 0. We use the following discretization scheme. Phi super n plus 1 sub m minus phi super n sub m over delta t plus u phi super n sub m minus phi super n sub m minus 1 over delta x is equal to 0. Phi super 0 sub m is equal to g of x sub m and equals 0, 1, 2, etc. M is equal to 0 plus minus 1 plus minus 2 and so on, where t super n is equal to n delta t, x sub m is equal to m delta x. It is possible to show that a condition of stability equation, reference goes here 2.42, sorry. In this case, take the form maximum value max of module phi super n sub m less or equal to C sub 1 max between m values of model G sub m. It means that the solution of the problem 2.46 should satisfy the condition max model of phi super n sub m less or equal to C sub 1 max of model phi sub 0 super 0 sub m, n equals to 0, 1, 2, and so on. Now the important formulation. Necessary spectral condition for stability. For the stability of problem 2.46 with respect to starting data, it is necessary that condition 2.49 be fulfilled, in particular when phi sub 0 sub m super 0 is any harmonic phi super 0 sub m is equal to e to the power I alpha m, where I is imaginary unit, alpha is a real parameter. In this case, the solution of problem 2.46 for initial conditions 2.50 has the form the following form: phi super n sub m is equal to lambda to the power n e to the power I alpha m, where lambda, which is equal to lambda of alpha, is determined by substituting expression 2.51 into the homogeneous difference equations of problem 2.46. Thus we get the following expression: lambda is equal to 1 minus r plus r e to the power minus I alpha, where r is equal to u delta t over delta x, and it is constant. For the solution 2.51 we may write max of model phi super n sub m is equal to model of lambda of alpha to the power n, max of module phi super 0 sub m. Therefore, if condition 2.49 is to be satisfied, it is necessary that for all real alpha we have the following expression. Module of lambda of alpha to the nth power less or equal to c sub 1. Since this condition must be satisfied for any value of n, it is equivalent to the condition module of lambda of alpha less or equal unit, less or equal 1. Precisely, this is the necessary spectral condition of von Neumann, as applied to the example under consideration. Let us now use the above formulated criterion to analyze the stability of problem 2.44. The spectrum 2.52 constitutes a circle with a center at the point 1 minus r and radius r in the complex plane. In the case r less 1, this region lies inside the unit circle and is tangent to it at the point lambda equals 1. For r is equal to 1, it coincides with the unit circle, and for r more than 1 lies outside the unit circle, as you can see on figure 2.5. Correspondingly, the necessary condition for stability equation goes here is fulfilled for r less or equal to 1 and not fulfilled when r more than unity. We can show that the necessary von Neumann stability condition turns out to be sensitive enough in this particular case, so as to separate preciously the region of stability from region of instability. If the necessary von Neumann condition 2.55 is not satisfied, then one cannot expect stability for any reasonable choice of norms. And if it is satisfied, one can hope to achieve stability for some reasonably defined norms. Parameter r, which is equal to u delta t over delta x is called current Friedrichs Levy number, or CFL, equivalent to U delta t over delta x. And condition CFL less or equal to unity is called current Friedrichs Levy condition. A similar analysis for case U less than 0 shows that for the discretization scheme 2.46, the condition 2.55 is not satisfied at any values of parameters, and therefore this scheme is always unstable. For this case, for a problem 2.44, the following discretization scheme will be stable. Phi super n plus 1 sub m minus phi super n sub m over delta t plus u phi super n sub m plus 1 minus phi super n sub m over delta x is equal to 0. And it can be stable on the following condition: CFL, which is equal to model of u delta t over delta x less or equal 1.